shorthand for binary, octal representation, and then hexadecimal representation. Okay. From hexa, 16 bits, octal 8 bits, we go on 32 and 64, work similar. Then what we did, we learned arithmetics in binary. Arithmetics in binary means, okay, firstly, instead of, okay, not the arithmetics, but what did we do? We learned how to convert between decimal to octal, or decimal to binary, decimal to hexadecimal, and vice versa. Right? We learned the conversions. Okay. With that, then we learn arithmetics. If you want to add two binary strings, how you do that? If you multiply two binary strings, how you do that? And similarly, okay, if you can do addition and multiplication, division and subtraction are similar. Subtraction is similar to addition, and division is similar to multiplication. It's just opposite to that, right? For example, if I divide 2 on 3, 2 divided by 3, it is the same as 2 multiplied by 1 over 3. Then we notice that we don't have to have an additional operation in circuitry, so therefore we only require addition as an operation, we don't require subtraction as an operation. Then we learn how computers store integers, how we store them in there. So we performed that on, for the integers, the storage we said, all right, if it's a positive integer, we'll start with 0, and if it's a negative integer, we'll start with negative, or with 1. Okay? And the remaining 7 bits or 15 bits, whatever you want to say, those would be of the binary representation. So that is substantially different to what we're going to do today. Today we are going to deal with how computers store real numbers. Real numbers means numbers with decimals, like 1.4, for instance. We didn't deal with this so far in the previous lecture. In the previous lecture, we learned how computers store integers, okay? Like whole numbers. That may well be like negative 14, positive 14, positive 16, so these kind of numbers. Okay. So now today what we want to do, we want to do computer representation of real numbers. And for that we would start with the 32 bits. We need slightly more accuracy. We still can do 16 bits, but we will start with the 32 bits and see how we go. Towards the end of last lecture, we learned normalized binary exponential form. Can anyone remind me what is normalized binary exponential form? Yes.
10 into 0.1 that's 2 to the power of maybe 2 or whatever.
Yeah, that's right. So normalized binary exponential form is you have a number between 0.1 and 1, okay, multiplied by 2 to the power some number. Okay, this is called normalized binary exponential form, and this is how you write it down. Yeah. So firstly, whatever number we got, a real number, we'll convert that into binary form, right? First step is to convert it and then to store it. And how it would be. Let's go over it. Okay. In this exponential form, binary exponential form, m is the significand. It has to be between 0.1 and 1 in the binary representation. Between 0.1 and 1, and the exponent e is a decimal integer. It could be any number, of course, any integer. So, for instance, this number 1101.01, this 2 indicates that it's binary. Okay. This is not normalized binary exponential form because this number is not in this range. Okay. To bring that in this range, I move the decimal to the left. If I'm moving decimal to the left, how many digits I moved? 1, 2, 3, 4. So this would be 0.110101 times 2 to the power 4. So step 1 is that always in the binary representation, we'll write the number in normalized binary exponential form. Right. And similarly, this number is not in the normalized binary exponential form. Can you tell me why? Absolutely. The significant, this thing is less than 0.1. It has to be between 0.1 and 1. You're absolutely right there. So I would move this decimal to this place. So if I move right, then the power will become negative. If I move left, then the power will become positive. Okay? And you count how many decimals, how many positions you move. So 1, 2, 3, 3 positions I moved, and I put decimal here. That means it's 2 to the power -3. Any questions? What is 1/6 of a 46? One sixth of a 46. It's 46, not 36. Why am I asking that? Because we're going to do.
It's 7 and 3 quarters.
What?
It's 7 and 3 quarters.
7 and 3 quarters? No, 11 and 3 quarters. It's 1/6.
Of 46.
Yeah. So you will have 7 and 4/6, which is 2/3, which is 6.666, 7.66666, wherever you want to start. Right. Now, coming back to with this, why I ask questions, because this brings you these kind of calculations in your head. As we have seen in the last 2 weeks, we are continuously multiplying, dividing, and doing these minor arithmetics rapidly. So these small questions helps in the end. Now, representing a real number, step 1, we convert that into normalized binary exponential form, NBE. And we used 32 bits for that. We can do 64 if we like, but the process is similar, so we don't have to go into it. So, as always, the first bit is a sign bit. Okay? Then the remaining bits are divided between exponent and the significand. Remember, what our number was? Number was m times 2 to the power e. So this is your significand, right? And that's your exponent. So first bit is for the sign bit. If this number is positive, then you have 0. If this number is negative, then you will have 1. Okay. The first bit gone. Then remaining 31 bits are divided between significand and the exponent. Right. So the number of bits used for the exponent determines the numbers that can be stored, number range that can be stored. And the number of bits used for a significand determines the precision with which numbers can be stored. So precision and basically range we are after. So what's the typical scheme? For a fixed number of bits to represent a real number, there has to be a trade-off between range and precision. Of course, I'm splitting 31 bits into range and precision, so I can move around. I have some flexibility. Right? So a typical scheme for representing a real number in 32 bits is sign 1 bit, exponent 8 bits, okay, and then significand 23 bits. if bits are not, if the numbers are not occupying that much space, then we add extra trailing zeros in it to make them those occupy bits. Okay, let's do some examples. But before that, we don't directly store exponents. For example, in some of the questions, you notice that the exponent was 2 to the power 4, for example, it was 4 or -3. We don't exactly store 4 there. Instead, we use a characteristic. Okay, what's a characteristic? So, characteristic is exponent bias to the exponent. You add that to the exponent. What that means, if I have 8 bits available, as you can see, if I have 8 bits available for exponent, what I would do, I would add exponent bias to that exponent. So, in other words, if I have 8 bits available, I would add 2 to the power 7 minus 1 plus the exponent, whatever the exponent is. Whatsoever. If the exponent was 4, I would 4 plus 2, 7 minus 1. Think of that as just a constant. Okay. That will give you the characteristic for that, and we will store that characteristic instead of just the exponent. What that means, I'll do some examples in a minute, and it will be very clear. So look at this number. So we want to represent this number in 32 bits. Okay, just try to understand this. There are only 2 steps you have to follow, only 2. Okay. And what those, how are we going to store them? First of all, notice that it's a positive number. So first bit is gone, it's 0. Right? Then, next, 8 bits are used for characteristic, and exponent bias is given to you. Right? So characteristic would be, we have 8 bits here for characteristic. This is the characteristic here, 8 bits for that, and then comes the significant. 23 bits. Significant is given to you, right? Done. Nothing. What you going to do? What actual part you have to do? You only have to find what characteristic you got. And you're given exponent 4. So characteristic would be 2 to the power 7 minus 1 plus this value 4. And what that number is? 128 minus 1, 127 plus 4, 131. Right? You agree with me? So that is your characteristic. So this is 2 to the power 7 is, let me write it down as 2 to the power 7 plus 3, because it makes representation a lot easier. 2 to the power 7 means you have number 1, 2, 3, 4, 5, 6, 7. Okay? 1, 2, 3, 4, 5, 6, 7. Yeah. Did you agree with that? That would be the number. Plus 3, which is 1, 1. Yeah? You add them up, what you got? Yeah? That's your binary representation of 131. And these are your 8 bits. This is how you represent a real number. So what would be the 0.101110101 2 times 2 to the power 4? It will be represented as 0 for the sign bit, then 8 bits for the characteristic, then the significant, which is 10110101. Yeah. But I need 23 bits here, not just whatever number written. How many bits there? 1, 2, 3, 4, 5, 6, 7, 8, 9, and remaining 14 would be just trailing zeros to make it 23 bits. This is how, in a 32 bits scheme, I would represent a real number. What you have to do in all of this, step one, you have to convert everything in binary, normalized binary exponential form. For this example, it was already converted into normalized binary exponential form, so we didn't have to do anything. Step two, we find out whether the number is positive or negative. It's a positive number, so 0 bit for the first, for the sign bit there. Then the significant is here. The only step that you have to do is to find what is a characteristic. How you get characteristic? Characteristic you get by adding this exponent with the exponent bias. Exponent bias you get from the bits available. Right? Since I'm dealing with 8 bits, so exponent bias would be 2 to the power 7 minus 1. And that's it. Yeah? So all of this step by step explained here, exactly the same way as I just did. So you'll end, so this is the sign bit, then this is the characteristic, and then that is your significant, which is exactly this number, which is exactly this thing. Add extra zeros to make it 23 bits. Any questions? Okay, so you can see that how quickly now you're converting integers into binary. So you should be on top of all of those calculations in your head. As you can see, it was 131, so what I quickly did, I wrote it as 128 plus 3 to get the binary. As you can see here, 2 to the power 7 means 1 and then 7 zeros. And this 3 means it's just 1, 1. I added them up and got quickly that binary representation here. Right here. So what's the method? Again, the method for finding representation of real number is for a decimal number convert to binary. So in the previous example, it was already given to us in binary, but normally it would not be given to you. So you would have to convert a number into binary. How you would convert a number into binary? Suppose you have 2.75. Yeah? How you would convert that into binary first?
Is that in decimal?
Yeah, 2.75. It's decimal. And since nothing written here, so it is base 10. How you convert that into binary? Absolutely right. So the binary representation would be, what next? 0.0 first. If I multiply that with 2, it would be 150, so 1 would come there. And then I would multiply again with 2, I would get 100, so 1 goes there. So this is my binary representation of 2.75. So I want to store it. I want to represent this real number in 32 bits. How are we going to do that? First step, I would convert that into normalized binary exponential form. That would be 0.1011 times 2 to power plus 2. I would move this decimal here. So this is my binary exponential form. It's a positive number, first bit is 0. Then second 8 bits are, the next block of 8 bits would be the characteristic. How you get characteristic? Characteristic would be 2 to the power 7 minus 1 plus this exponent 2, which is 2 to the power 7 plus 1, which is 1, 0, 0, 0, 0, 0, 0, 1. Agree? Yeah. And then the last 23 bits are the significant, which is 1, 0, 1, 1 so far, and that's 19 zeros to make it 23 bits. Okay, extremely simple steps. Don't forget to convert that into binary and then find characteristic, which you always get by exponent plus exponent bias. Remember, exponent bias, you get it from the number of bits available. If I say that, okay, there are 10 bits reserved for the characteristic, then the exponent bias would be 2 to power 9 minus 1. Okay. But throughout in this subject, we will only deal with 8 bits, so that's fine. So let's look at more examples. Find out 32-bit representations of the following numbers if 8 bits are used for characteristic and exponent bias. Is this. So can you solve this question for me, please? So that's my solution. Could be wrong. I just want to test myself whether I'm correct or not. So how many of you got the same answer as me? No one? One person got the same answer as me. I was starting to think I must be wrong then. looks like that I'm wrong.
The same thing with the 0 in front of the last bit.
0 in front of the last bit. Why? So you got 0 here.
Yeah.
Why?
How it works it out.
No, but that's given to us, right? That's given to us. Don't count this 0. Right? Because this is useless. This doesn't count. Even if you put million zeros there, these are just zeros. Left and just like if you are to say, okay, $10, okay, and you say $10, right? You write it like this, right? These are $10. These are still $10. Okay. So if you put zeros on the left, doesn't matter. Ah, yes, 0 on the right. Of course, that does matter. Yeah, people would still pay if you charge them 100. Yeah. Okay. Anyway, well, I can see if you didn't tell me the answer yet, that means either you're struggling with it or you're not confident. Anyway, this is my solution. As you can see, first 0 for the sign, and then I have for the this is my characteristic, right? And after that, this number is given to me significant. In this entire process, nowhere there is only one step I have to do. That is characteristic. Find the characteristic in binary. Nothing else. If you can do this, there will be one question in test 1 about this. So you should be confident that you can do that. Now, look at this number. By giving this example, I want to prove one thing to you, that nothing is perfect. Nothing you're getting is extremely precise, the process I mean. There are always places for more precision, requirement for more precision. So, look at this number, negative 2,365.66, whose binary representation is this. I'm not asking you to convert that into binary because we already done that. I want to store this in computer or represent that in real numbers, let's say. If I want to do that, first of all, I would have to write it down as normalized binary exponential form. So I would have to move that decimal so that the number is between the range. Okay. Now, how many places I moved? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this number would be negative 0.1, then 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, and then 1, 0, 1, 0, 1.
We can't see what you're doing.
Well done. Thank you. 1, 1. No, so far I didn't do that. I've done it just now. Right. Okay. Well, what happened? So I moved this decimal to convert that into binary exponential. Right? 12 places to the left. So this would be 2 to power multiplied by 2 to power 12. Yeah? Positive 12. Now, what that means now, I have all this big string as significant there. So I have a big string of significant, but I can only use 23 bits for that. So 8 bits goes for the characteristic, which is 2 to power 7 minus 1 plus this number 12, which is 2 to power 7 plus 11, right? Yeah. Which would be 1, 0, 0, 0, and then Is that right? Yeah. So this is your characteristic. Right? I have got 8 bits for that. 1 is for sign bit. So 1, because number is negative. And then this characteristic goes in there, 8 bits. Yeah. So the first 9 bits gone. And the remaining 23 bits is this string. And then from there you can see that so the computer representation of real numbers may not be exact because the number was continuing. We don't know what is here, here or here. So up till then it is 23 bits, but if it is 1 there or 0 there or 1 there, somewhere there, these 3 bits will be missing. So these will not be represented. What that means? That means the number we are trying to represent would not fit in 32 bits. So it's like an overflow problem. You need 64 bit for that, so that you can go for more precision. Remember, this represents precision. So for more precision, you can add extra space, like say, go for 64 bits, and then you will have you can reserve 16 bits for the characteristic and remaining for the significant. So these 3 bits or whatever bits are in the end would not fit in there. Do you agree with me? Okay. So far we have not calculated range of numbers that can be represented on 32 bits computer. If I ask you to find the range of real numbers that can be stored, can you do that? Or represented? I'm sure you can, and exactly we have to use this formula that we have normalized binary exponential form to find their range or possible values. How we go? How we do that? I'm going to do that soon. So what we've seen that the computer representation of a real number may not be exact, but the errors are very, very minor, very, very small. Also, round-off errors can occur in computer arithmetic with real numbers. Okay. For example, I gave an example of calculator several times now. That if you have only 10 bits available and you want to store, you want to represent a number which is 11 bits, then it will show an error. Okay? So for example, if you pick 2 big numbers and multiply them, soon you will see that there is an error because the resulting sum is big enough. It's quite big than the computer or the calculator or anything that can handle. That doesn't mean it's incorrect. It means it's just showing an error. So distribution contrasts with integers which are stored and manipulated exactly. Because of slight imprecision in the way computer handles real numbers, care is needed in a computer program if testing whether 2 real numbers are equal. Of course, then we would have to be very, very careful because we are talking about long string of bits there. Anyway, so as I just said, what range of numbers can be represented? Think of that, assume real numbers are represented in 32 bits with 8 bits for the characteristic and an exponent by or to the power 7 minus 1. So remember, 8 bits. If you have 8 bits available for the characteristic, can you find out the range? So 8 bits means you can have 0, 0, 0, 0, 0, 0, 0, 0. This is the 0 number, or 1, 1, 1, 1, 1, 1, 1, 1. These are all the possible values. Yeah? You agree with that, right? So this is from 0 to 255. Yes? So between 0 and 255 for the characteristic, but that characteristic goes in the power of 2 to power, I mean. So what that means, That means since the characteristic is exponent plus bias, so exponent plus 127, but the characteristic possible values are between 0 and 255, so basically your range is between negative 127 to 128. So this characteristic can have range between negative 127 and positive 128. How did I get that? For example, when the characteristic, you put 0 here, 0 is equals to exponent plus bias. Bias is 127, so you take to that number to the other side, which implies negative 127 is equals to exponent. Yeah? So this is the minimum value you're going to get. What the maximum value you're going to get is when you put 255 here is equals to exponent plus 127, which is equals to 128. So exponent's maximum value is 128 and the minimum value is negative 127. That's huge. Yeah? So 2 to power, think of that. Think of that, 2 to power 128, how big that number is. So that big number can be represented here. Okay. What's the smallest number then? 2 to power negative 127 is a very, very small number. Similarly, the significant, those 23 bits, it can range from the smallest value, which is 0.1. Yeah. It can range from the smallest value, 0.1, to the maximum value, which is going to be whatever when you have all of them as string 1. And what is that value? If you keep calculating that, it would be, let me actually have done that. So it is half for the first, then this is 1 over 2 squared, that is 1 over 2 to power 3, that is 1 over 2 to power 4, so on, which is extremely close to 1, but not just 1. It's very, very, very close to 1. So the significant range is between 0.1 and that value 1. So let's look at the range of numbers that can be stored. Okay. Smallest significant times 2 to power smallest exponents. This is the smallest number you can store. And smallest significant is, sorry, I was wrong there when I said 0.1. Where is it? When I said 0.1 here, it is not actually 0.1, it is 1 over 2. This first and rest are zeros. So it's half. Okay, so the smallest significant times 2 to the power smallest exponent. We calculated smallest exponents to be negative 127. So 0.5 times 2 to the power negative 127, which is 2 to the power negative 128. Do you know how you got that? So what I mean is, here it was 2 to the power negative 127, but here I wrote 2 to the power negative 128. How did I do that?
You apply 2 to the minus 1.
Yeah. So what I did, this 0.5 is actually 1 over 2. So when this goes in the numerator, its power would subtract. So that would be 2 to the power. So the smallest value that can be represented on 32-bit computer would be 2 to the power negative 128. Now, can you calculate the largest possible value? You think what that would be? 128. 2 to the positive 128. Largest significant, which is extremely close to 1, times 2 to the power largest exponent, which is 128. So on a 32-bit computer, you can represent numbers between 2 to the power negative 128 to the 2 to the power positive 128. massive. So suppose I ask you not to write it 2 to power and write as 10 to power. What do you think the number could be? So at the moment the range is between 2 to power negative 128 and 2 to power 128. Suppose I want to write it down as 10 to power. Do you think what the approximate numbers would be, these powers? Instead of 2 to power, suppose you want to write 10 to power, which is more usual way of writing in exponential form. Rough guess. So, in the real case, if you write 10 to the power, the minimum value that you had is 0.294 times 10 to power negative 38 and positive 0.340 times 10 to power 39, which is quite big. 10 to power 39. It's huge. But if a number that you're going to represent in 32 bits is bigger than 0.34 times 10 to power 39, then there would be an error. Your computer will refuse to handle it if it's 32 bits. Right? If it's 64, of course it can handle if it falls in range, but then still the overflow will occur and underflow as well. Likewise, the negative numbers, you can put negative there, and yeah, we only explain for positive, and you can do it with the negative numbers as well. Just like when we did the integers case, we done overflow and underflow. Same things happen. If the result of a computation is outside the allowed range, overflow or underflows occur. Overflow means the magnitude of the number is too large for the computer. For example, if you have this number is too large on a 32 bits computer, the maximum power it could have is 39, not 41. Similarly, underflow, if the number negative 39 is there, but this number is outside the range, it has to be close to 0.29 or something. So that is small, too small for a computer to handle. So it's it's under full problem. Note that we have not dealt with zeros here. You need special entries for zeros, and that would be 32 strings of zeros. Yeah, 0, 0, 0, 0, 0 to store. So that's a special case. So this is because 0 can't be written in the normalized binary exponential form. So other schemes to represent real numbers, what are them? In practice, variations on the scheme we have discussed are often used. What other variations you can think of? Suppose you want to improve precision on a 32-bit computer. How you can do that? What are the possible ways you can do it? Yeah, that's a fantastic answer, actually. If you are absolutely sure that you're not going to use all the bits reserved for the characteristic, right? Then you can move some of the bits to the significant to get more precision, right? Remember, what characteristic is telling you the range of numbers that you're going to store. If the range of numbers you know that you're going to store are not big, small numbers, however significant is quite a lot, then you can improve that accuracy by allocating some of the bits of the characteristic to the significant. Also, if you are absolutely sure that you're only handling positive numbers, then the first bit is redundant. You don't have to put every time 0 there, right? So first bit is not used at all in that case. So you can put that extra bit to the significand if you like. Or you can increase range if you like in that case. By giving that, putting that 0 for the 9 bits of characteristic. If you know that you want to increase your range of numbers to be stored, right, by putting an extra bit there would give you, instead of 2 to the power positive 128, you will move to 2 to the power positive 130 maybe, instead of 128. You would have slight jump, right? That slight jump will give you slightly wider range. So you can do the trade-off between bits available for characteristic and the sign and the significand to get more precision or more accuracy or more sort of range. So these things can be manually done. But still, it will not give you whole sort of range. At the moment, your range is 10 to the power positive 39, right? But even if you move all of your characteristic to significant, sorry, not characteristic. So all of your significant to characteristic, still there would be a bound. And after, beyond that bound, there will be an overflow problem or underflow problem. And for that, you would have to increase to like 64 bits or 128 bits if you want. But then again, in the end, you have to keep in mind this is finite. It's not that, okay, you keep doing and you can do forever computations. It has to terminate at some stage. So yeah, these some examples are written here, and yeah. So this is what we are here in these conversions into binary. So far we did binary arithmetic throughout in the first 7 lectures. And in this, as I said, we started off with the integer conversion to binary, binary to integers, then real to binary, binary to reals, and then shorthands of binary, which were octal and hexa, and how arithmetic's been done, how these are stored, how to represent these numbers in computer. So in the next lecture, tomorrow, we'll start a new topic, logic. There will not be these kind of new calculations there, but similar kind of tables and truth values that we're going to do. I personally like that topic a lot. There's lots you can talk about. Anyway, any questions, please let me know, and don't forget to practice all of these questions. You don't practice, you forget it. Sure. Yes, Mike. What's that?
Yeah, and then I think I'm shooting off. I mean, that's what happened when you get boss. Because last time, I skipped 7, and then anyway, I give you 5, 7
Yeah?
yeah. Do you go for a run every morning?
No, not for 2 weeks now, but normally I do.
I mean, on the treadmill I can't run because my balance.
On the treadmill?
Yeah, I've got balancing coordination issues.
Hey, so I just can't make it to the next class tonight. You have an extra
Yeah, sure.
You on echo?
Yeah.
Yeah.
If not, I can send you the other recording I have.
And also next week, I know.
Tomorrow?
Yeah. Not tomorrow, 2 classes. There's 1 class next week. I'll be able to make it because I've got an email saying I have to attend this thing at the trial.
That's
I'm